All right, so this is the first recorded lecture for our class. And so let me just get the slide set up. Right. Right, so we can go over some more of the logistics surrounding how everything will work online during the meeting, during our lecture time tomorrow morning. And I'll also be communicating with you over email throughout the rest of the semester. Right, and so as I mentioned before, the general plan will be to have pre-written slides, which are set up on the video now, and I'll go through uh, lectures, go through the slides and lectures that will last about 35 minutes on average, most likely. And so this is, as I mentioned before, this is going to be at a slightly faster pace than what we were doing in person, just because I can move through the material a lot faster when I'm not writing by hand and when there are no questions. But since you can always sort of rewind the lectures and pause them and work on things in the middle, that should hopefully help the pace or help you deal with the pace. Great, and so we're sort of in the heart of chapter 7, which is all about probability theory. And so we've seen a few simple examples, and well, sort of on the last Friday, we were supposed to have a lecture about probability distributions, which instead I sent you a handout of lecture notes, which hopefully you've read. So for this lecture, I'm assuming you've read the file I sent you about probability distributions. And so what we're going to talk about now is two of sort of the most important concepts sort of at the basis of probability theory, which are first conditional probability and then the notion of independence. And so time permitting, we'll also talk a little bit about the binomial distribution, but if we don't make it, then I'll do that the next lecture. Right, and so what is conditional probability? We can begin with a simple example. And so sort of the basic idea is, well, for certain problems, we may want to know the probability of an event that occurs given certain information that we already know. And so sort of a simple example is, let's suppose we flip a coin 3 times in a row, right? So you're looking at all possible outcomes of flipping a coin heads or tails if you flip it 3 times. Well, let's suppose we know that the first flip is a tails, and we want to calculate, given that information, that we flip an odd number of tails, right? So we flip the coin once, we've seen its tails, and we want to know, given that information, what's the probability that we will flip an odd number of tails. Well, what you can do, since we're only looking at 3 flips, we can just sort of list out all the possibilities, assuming that the first flip is a tail. And so I have those listed out here. There are 4 different possibilities. Right, and so we're interested in, well, how many of these do have an odd number of tails, given that the first is the tail, and we can just count that there are 2 of them, right? So when you flip tail and then 2 heads, or when you flip 3 tails in a row, right? And so just sort of given our intuition about really using the uniform distribution, well, I have 4 possible sequences of flips that begin with a tail, and out of those 4, 2 of them have an odd number of tails. So if we just divide the number of events which have an odd number of tails by the total number of events that begin with a tail, well, we're going to be dividing 2 by 4, and so we would expect that the probability is just that ratio, which is 1/2. Right. Right, and so the idea is, we, instead of looking at the whole sample space of all sequences of 3 coin flips, what we've done is we sort of just restricted our attention to the subset where we're only looking at events that begin with a tail, and we sort of treated that as our new sample space when we calculated the odds. And so this is sort of basically how conditional probability works. And so what we're going to do now is go through the formal definition, or the rigorous definition. And so let's say we have a sample space with some probability distribution, and we have 2 events, say E and F. And let's also assume that the event F has a positive probability of occurring, so that it makes sense to talk about it. And so what is the definition of conditional probability? Well, it's defined to be using this symbol over here. You write whatever your distribution is, and then you have the set E that you want to know the probability of, and then a vertical bar, and then the set F, which you're sort of assuming. and you take the probability of the intersection of E and F, and you divide it by the probability of F. And so this is sort of read as the conditional probability of E given F. Right, so this is the formal definition. Of course, it may not be like immediately obvious how this definition connects to the example we just saw, but I'll go through that in a second. And so notice this is where sort of the role that the assumption that the probability of F is bigger than 0 is appearing, because otherwise we couldn't divide by F, right? And so sort of how do you think of this intuitively? Intuitively, if you look at the intersection of the two events, E and F, you're sort of thinking about the event where they both occur. And so since we're already sort of assuming that F occurs, you have to sort of divide out by that to normalize it properly. But maybe this will make more sense when I look at an example. Right, and so let's return to the coin flipping example where we flip a coin 3 times in a row, and we're assuming that the first flip is tails. And we want to calculate the probability that an odd number of tails appear. And so let's do this more precisely using the definition that we just saw in the last slide. And so in this case, our sample space is the set of all possible sequences of coin flips where you have 3 flips in a row. And we're just going to use the uniform distribution on the space because every single sequence is equally likely to occur. Right? And so you can calculate the cardinality of the sample space is 2 cubed, right? Because for each point in each sequence, you have it's either heads or tails, and there are 3 points. Right. And so what is our event F that we're conditioning on? So remember, F is the set of all outcomes where the first flip is T. And so notice we can calculate since we're using the uniform distribution, we can calculate the probability of F, which is, well, I have 4 elements of F, and my set S, which is the larger sample space, has 8 elements. So the probability of F is 1/2. And then remember, E, which is the event we want to know the probability of, is the event that contains all sequences with an odd number of tails. And so notice if we go back to the previous slide, notice that if you're calculating the conditional probability, you don't need to calculate the probability of E. You only need to calculate the probability of the intersection of E with F. And so in particular, we don't really have to, although we could, we don't really have to list out all the elements of E because we just have to look at the intersection with F, right? So if E is the event that contains all sequences with an odd number of tails, well, we can just look at the events in F that have an odd number of tails, and that's the intersection. And so you can just check that there are 2 of them, where you have tail, heads, heads, and then 3 tails in a row. And so therefore, well, what is the probability of this intersection? We have 2 elements, and we're dividing by the number of elements in the sample space. So it's 2/8, which is 1/4. Right, and then if we just use the definition from before, we get that the conditional probability of E given F, well, I take probability of E intersect F, which is 1/4, divided by probability of F, which is 1/2. And if you calculate that, you get 1/2, which is what we saw before. Right, so this sort of formal definition matches up with the more intuitive example from before. Right, and so I want to do another example involving drawing cards of how you would calculate conditional probabilities. And so in this case, we're going to be looking at, say, working with a standard deck of 52 cards, and we're assuming it's been shuffled randomly. And so when you see these words sort of shuffled randomly, that indicates you're probably going to be working with the uniform distribution because basically every outcome is equally likely to occur, which is what the uniform distribution is. And so the question is, well, let's suppose I draw a 2-card hand, and suppose I know that the first card that I draw is an ace, right? So this is sort of information that I'm given, or that information that I'll condition on. And so the question is, what is the probability that you draw a 2-card hand with 2 aces, assuming that your first draw is an ace? There are a few ways to answer this question. You may be able to even model it and just answer it without using conditional probability, but we'll use the conditional probability setup we've been talking about. Right, so in this case, our sample space, sort of going into a little bit more detail, is the set of all possible 2-card hands that are drawn from a standard 52-card deck. For example, the elements could be like you have an ace of hearts and then a 2 of diamonds, or a 3 of clubs and then a 4 of clubs, or something like that. And each such pair is itself an individual element. And since we're talking about sort of drawing one card after another, the order matters, right? So the event where you draw an ace of clubs and then a king of hearts is a different event than if you do the reverse, where you draw a king of hearts first and then an ace of clubs. So we want to make sure we take order into account when we're calculating everything. Right, and since, as I said before, since each two-card hand is equally likely to occur, we're going to use the uniform distribution on our set. Right, and so let me just start labeling everything, which is again how you begin with all these problems. So let me let A denote the set, which is a subset of S of all ordered two-card hands that begin with an ace, meaning the first card that you drew in that event was an ace. And so notice we can calculate the cardinality of A just by multiplying 4 times 51, which is 204. And so remember, why is this true? Well, think about the first card has to be an ace, and there are 4 possibilities for the first card. So I have 4 choices there. And then once I draw an ace, there are 51 cards remaining in the deck. And so there are 51 other possibilities for the second card. And so you have to multiply these two together, as we saw several times when we were talking about counting problems in chapter 6. So you get 204. Right. And so I've just typed that out here. Right, so again, our sample space is the set of all possible two-card hands, and then the set A is the subset consisting of events where the first hand or the first card was an ace. And now we're going to let E denote the event that we're sort of interested in understanding the probability of, where you draw 2 aces in a row. And so formally, E is going to be the subset consisting of all ordered two-card hands consisting of 2 aces. Right? And so similarly, we can calculate the cardinality of E. In the first entry, it has to be an ace, so there are 4 choices. And once you fix one of those, well, there are 3 remaining aces. So the cardinality of E is going to be 4 times 3, which is 12. Right? And so what we want to know is that given information in A, or conditional on information in A, what is the probability of E? Right? Well, remember that this involves looking at the probability of the intersection of E with A, although in this case, it turns out that E is actually just a subset of A, so the intersection of E with A is E itself. And so now let's just use the definition to calculate the conditional probability. So probability of E given A is probability of E intersect A divided by probability of A. Right, and since the intersection of E and A is just E again, this reduces to probability of E divided by probability of A. And so we're using the uniform distribution, so the probability of E is the cardinality of E divided by cardinality of S, and the probability of A is cardinality of A divided by cardinality of S. And so we'll notice that the terms involving the S will just cancel in the fraction, so this reduces to just size of E divided by size of A. And so that's going to be 12 divided by 204, given what we calculated before. And so if you work this out, you can see that you have about a 5.88% chance of drawing an ace, given that the first card you drew was an ace. So that would be the answer to the question that was initially posed. And so this example sort of, along with the previous one, I think illustrates sort of the main intuitive principle behind conditional probability, which is something I talked about earlier a few minutes ago, which is you're sort of working as if the set A, which you're conditioning on, is your new sample space, right? So you're assuming that you know information from A, or you know that something in A is going to happen. So everything outside A is irrelevant for the problem. And so this formula is sort of set up to allow you to treat the set A that you're conditioning on as your new sample space. And then here, since we're using uniform distribution, we're just looking at the size of E divided by the size of A, which is sort of what you would expect for a probability if your sample space was A. Right? And so you can make this observation a little bit more general, which I'll talk about on the next slide. And one more thing to point out is, notice we didn't have to calculate the size of the sample space S, right? So if you're conditioning on a certain subset of S, you often do not have to know the size of the overall sample space, which is helpful to remember for a lot of problems. Okay, and so here's a remark sort of summarizing a little bit more directly what I was just talking about. So let's say we have a sample space and a probability distribution on the sample space, and let's suppose, moreover, that it's actually the uniform distribution, meaning every element of S is equally likely to occur. Uh, then the probability of E given F, well, if I just use the formula, right, it's probability of the intersection divided by probability of F. But since I'm using the uniform distribution, that reduces to this expression. And then the terms involving S as before will cancel. So it just becomes the cardinality of the intersection of E with F divided by F. Right? And so this is a useful formula to remember that will make a lot of calculations easier. Unfortunately, this is only valid, remember, when P is the uniform distribution, or else this third step here would not work if it wasn't the uniform distribution, right? So keep that in mind. Okay, so that's basically everything I wanted to say about the basics of working with conditional probability. And so the next notion in the theory, which is related to conditional probability and sort of equally important, is the idea of independent events. And so I think this should be at least intuitively a little bit more familiar, even if you haven't seen probability distributions before. And so I'll begin by looking at this with another coin flip example. And so let's suppose we're just working with a fair coin like a quarter, and we flip it, say, 2 times in a row. And so the question is, well, what is the probability that the second flip is heads, given that your first flip was also heads, right? And so what do we expect? Well, we expect that since, I mean, every time I flip the coin doesn't understand what happened in the previous flip, so it should be just sort of the odds of flipping a heads regardless of what happened before. So we would expect that the probability would be 1/2 in this case, since you just have a 1/2 chance of flipping heads. Uh, and so sort of the idea of what's going on is, well, there's no interaction between your first flip and your second flip, and so they're somehow independent of one another. And so this is what this notion of independence is related to. Uh, right, and here's sort of a more formal model of just the same problem. So let's set it up with events. And so let's suppose F is the event where the first flip is a heads, meaning that, well, there's 2 choices. I could either do heads, tails, or heads, heads. And then we're going to let E denote the event where the second flip is heads, meaning E contains the elements tails, heads, and heads, heads. And so if we use the uniform distribution, and let's try to actually calculate the probability of E given F, which is sort of what I was asking originally. Right, well, we can just calculate, it's going to be the size of the intersection of E and F, which is just 1, because the intersection of E and F is heads, heads. And then divided by the size of F, which is 2, so we just get 1/2, which is exactly just the probability of flipping heads, which is what we expected. And so notice that right, so this is sort of just the probability of the event E, regardless of information involving F. So somehow E and F are independent of one another. So it doesn't matter how much you know about F, it doesn't affect the outcome of E. This is the main idea. Okay, and we can make this more rigorous now with the formal definition of independence. And so I think great, so we're going to work with a sample space S as before and some fixed probability distribution, which does not have to be the uniform distribution. And we'll fix 2 events, which are subsets of S. So I think this definition is going maybe not as immediately obvious necessarily as some of the other definitions that we've seen in probability theory, but I'll do an example that will connect it to your intuition. And so, right, so we have these 2 events, and so we'll say these 2 events are independent if I look at the probability of the intersection, or the probability that something in both of them occurs, and if they're independent, if that probability is equal to the probability of E times the probability of F. Right, so 2 events are independent if probability of E intersect F is equal to probability of E times probability of F. And if they're not independent, meaning this identity fails, which is going to be the case a lot of the time, then we say that the 2 events are dependent, meaning there's some like interaction or influence between the 2 events. And so just as a remark, which will hopefully make this definition a little clearer, let's suppose that I have two independent events and I try to calculate the conditional probability, right? So what does this conditional probability mean? We're sort of looking at the odds of E occurring given that F occurs, right? Given that we know information from F. Well, if the events E and F are independent, then it shouldn't matter what we know from F, because anything we know from F shouldn't have an outcome on E, since they're independent of one another. And so we can actually check that this is true formally. So if I use the formula for conditional probability, it's equal to probability of E intersect F divided by probability of F. But if the events are independent, I can replace the numerator by the product probability of E times probability of F, and then those terms are going to cancel out, and so I just get the probability of E left over, right? And so if the events are independent, then the probability of E given F is just the same as the probability of E, again, because F has no effect on the outcome of E. So that's what we expect. And so this line over here, this formula is the main sort of motivation for why we're using this definition for independence, because it connects well with the notion of conditional probability. Great, and so over here I've just written out sort of what I've said verbally. All right, so we'll see some examples. So we'll begin with an example, which is sort of an extension of an example you saw in the notes that I sent to you last week involving a weighted dice. And so let's suppose we have a 6-sided dice, and the face number 6, or sorry, the dice rolls a 6, say 50% of the time, and then each of the other faces is rolled, say, about 10% of the time. So the dice is heavily weighted to roll a 6. And so we're going to be looking at events involving rolling this dice twice. And so our sample space will consist of all possible ordered pairs of 2 rolls. And so if you want to model this mathematically, what you would do is, well, what is your sample space? It's sort of ordered pairs consisting in the first entry what you roll the first time, and then in the second entry what you roll the second time. So each roll you can roll any number between 1 through 6. And so since you're looking at ordered pairs, we can model the sample space by taking the Cartesian product of the set 1, 2, 3, 4, 5, 6 with itself, or taking Cartesian product twice. Okay, so notice that unlike some of the other examples we were looking at, you can't use the uniform distribution on S, because you're more likely in any given roll to roll a 6 than you are any of the other faces. So we have to use a different distribution, which will be a version of something we saw in sort of the simpler version of this example in the notes earlier. And so, right, so this may seem a little bit arbitrary what I'm about to do, but this turns out to be like a very accurate way to model these types of problems. So what I'm going to do is first define a distribution not on all of S, but just on sort of one of the components of the Cartesian product. And so I'm going to let R be that distribution. And so I'll define R of 6 to be 0.5, which gives me the odds of rolling a 6. And then for each other I between 1 and 5, I'll define R of I to be 0.1, which gives me the odds of rolling each of those individual faces. And so I'm going to define a probability distribution on the full set S of all events involving 2 rolls by setting, well, if I have any ordered pair where A is the first roll and B is the second roll, then the probability of that pair I'll obtain by taking R of A times R of B, right? Taking the probability of rolling an A and then multiplying that by the probability of rolling a B. So for example, if you consider the event where you roll a 1 and then a 6, the probability of that is going to be R of 1 times R of 6, or the probability of rolling 1 times the probability of rolling 6, which is, you can calculate as 6%. And so this is typically something referred to as a product distribution, right? Because you can check just by sort of adding up the values that this function R over here is a probability distribution, although it's only a distribution on the set 1 through 6. It's not a distribution on all of S. And so what we'll do now is just sort of double check that this function P is actually a probability distribution. Right, so let me just go through the proof. And so what do we have to prove in order to what do we have to show in order to prove that P is a probability distribution? We have to show that if I sort of sum up the values of P over all the elements of the set S, meaning over all possible ordered pairs of roles, that when I sum up all these probabilities, I have to get this exactly equal to 1. And so we're going to use the fact that if I just look at this other function R, that if I sum up the values of R from 1 through 6, then this is equal to 1, which we've already checked that in the last notes, but this is also sort of relatively easy to just check now if you want to. Right, and so what is this sum involving all the terms with P? Well, for each ordered pair, let's say the first entry is I and the second entry is J. Well, then P of rolling an I and then rolling a J is just going to be R of I times R of J. But then I have to sum that up over all possible pairs. So I is going to range from 1 through 6 and J is going to range from 1 through 6. So this is what I get as a result. Well, notice that if I fix I on the outside, then this R of I term doesn't depend on J at all, so I can factor that out. Right, and so if I factor out the R of I, I'm just going to be left with R of I times the sum of all the RJs, which I can then factor out of the sum over here, right? And so this sum that I started with in the first line just splits as a product of the of two individual sums. Sum from I equals 1 to 6 of R of I and sum J equals 1 to 6 of R of J. But both of these sums are equal to 1 by this observation we made before. And so the sum is just going to be equal to 1 times 1, which is 1. So this distribution, which I defined as sort of it's called the product distribution, is indeed a probability distribution. And this is what we're going to use to model the problem. Right. Okay, and so now let's look at some more examples related to this setup. So let's consider two events A and B. So the event A contains all possible ordered pairs where 4 is in the first entry, and the event B contains all ordered pairs where 6 is in the second entry. And so sort of less formally, A is just the event where your first roll is a 4, and B is the event where your second roll is a 6. We expect these to be independent because, well, it doesn't really matter what your first roll is. The odds of rolling a 6 on your second roll should not be affected by whatever you rolled the first time, and vice versa. And so let's actually check using the definitions that these are independent, right? And so we need to show that the probability of the intersection of A and B is the same as the individual probability of A times the probability of B. So let's first do that by calculating probability of A and probability of B individually. Right, and you can check just using, again, the definition of P, that probability of A, I'm just summing up the probability of each individual element of the set A. And so for each of those, I'm going to have R of 4, because the first entry was a 4, times R of whatever the second entry was. So that's going to be the sum from I equals 1 to 6 of R of 4 times R of I. But notice I can factor out the R of 4 from the sum because it doesn't depend on I. And then the sum from I equals 1 to 6 of those terms is just going to be equal to 1, as we saw before. So the probability of A is actually just R of 4, which is 0.1. And so notice that actually the probability of the whole set A is the same as just the probability of rolling a 1. Or sorry, excuse me, of rolling a 4, not rolling a 1. And so using basically the same calculation, you can also check that the probability of B is 0.5, which is the same as the probability of just rolling a 6, regardless of what else has happened. And so if you want, you can just sort of pause the video and just do that calculation very quickly. It should just be very similar to what I have written up here. Right, so now we know probability of A and probability of B, and to check independence, we have to compare that to the probability of the intersection of A and B. Well, what is the intersection of A and B? You can just check by inspection that the only element that's in both of these is the element 4, 6, right? Because you have your first roll has to be a 4 and your second roll has to be a 6. So there's only one way that can happen. And well, if I remember the definition of P, what is the probability of this event? It's just going to be R of 4 times R of 6, which is 0.1 times 0.5. but we just saw that that's the same as probability of A times probability of B. And so these events are independent. Okay, and so now I also want to, just using the same sample space and the same distribution, let's also consider two events which are not independent or which are dependent. So I'm going to let A continue to be the event where the first roll is a 4, and then I'm going to let C be the event where you roll 2 6s in a row. So C is just the set containing the one ordered pair with 2 6s in it. And in particular, the probability of C you can calculate is 36% or 0.36. Right, and so the event A, again, is the event where your first roll is a 4. And so since in the event C, you know that you're rolling 2 6s in a row, you can't expect them both to occur, right? And so if you sort of assume something in A occurs that influences the outcome of C, and in particular tells you that C can't occur if something in A occurs. So there's some sort of relationship between the two events. So we don't expect them to be independent. In particular, we expect them to be dependent. And you can check, again, just the main point here is, I mean, intuitively, this is hopefully obvious, but you can check more formally using the definitions, that if I look at, well, what is the intersection of A and C? Since there's no common elements between A and C, the intersection is just the empty set. And so the probability of A intersects C is 0. However, if I multiply the probability of A times the probability of C, that's definitely not 0. And so therefore, probability of A intersect C is not equal to probability of A times probability of C. And so the events are dependent. Okay, and so there's just a little bit more related to independence that I want to elaborate on, and then we'll finish up the lecture for today. And so this is related to sort of, so everything we've been looking at so far just involves two separate events, and so now we're going to be looking at sort of collections of some arbitrary finite list of events. And so let's suppose we have a sample space, and suppose we have some sequence of subsets of S, or some collection of events in S. And so these events are said to be pairwise independent if any two such pairs of events are independent, right? So if, say, I pick E1 and E7, then those two events are independent. And that's also true just for any pair that I pick. And so there's another notion which is somehow a stronger notion of independence, which is called mutual independence. And so this is a little bit more complicated. So the events are said to be mutually independent is if, when I look at the probability of the intersection of all of them, of intersection E1, E2, et cetera, up to En, then that splits as the probability of E1 times the probability of E2, and so on up until you hit the probability of En. Right, so a set of events is mutually independent if the probability of their intersection is the product of the individual probabilities of each of them occurring. And so this is, in fact, sort of a stronger condition than the notion of pairwise independence, although it's not immediately obvious that that's the case. So we'll look at an example in a second. Before that, though, one way to think about this, I think that helps is consider like the problem of, say, flipping a coin, say n times, and let's suppose that EI is the event. Say you flip heads on your ith flip, or it's the event you flip a tails on your ith flip, right? And so you can check using this definition, although it takes a bit of work, that these events are mutually independent. I mean, the idea is that whatever you flip at the ith point in the sequence of flips is not really related to what's going on at any of the other points in the sequence, so they should be independent in the stronger sense. And you can sort of check it if you use a product distribution similar to what we looked at in the last example, although I'm not going to do that in these notes today. Right. And so let's look at one more example related to this. And so again, we'll be looking at the sample space consisting, instead of, say, n flips, let's just set n equal 3 for simplicity. and we're flipping a fair coin with the uniform distribution, and we flip it 3 times. And so we're going to consider 3 separate events, which I've listed out here. And we're going to sort of consider, well, are they mutually independent or pairwise independent or not? So E1 is this event. So notice that in E1 is the event of all sequences of flips where the first flip is a heads. If I look at E2, you can sort of, looking at it for a minute, you can see that E2 is the event where the third flip is heads. And on the other hand, E3 is a little bit more involved. E3 is the set of events where either the first or the third flip was a heads, but not both, right? So for example, heads, tails, heads is not in this set, even though it's in the first 2, right? Because so I can only have either the first or the third be heads in E3, but not both. So these are sort of 3 separate events. And so you can check as sort of a simple exercise, maybe if you want to pause the lecture right now to check this, that these events are pairwise independent. Right, and so just go back to, right, you just want to check that if you pick any 2 of them, that if I look at the intersection, I can compare the probabilities in this way. It's not too hard to check that for this example. The aspect that's a little bit more interesting is that these events are in fact not mutually independent. And in fact, that's actually relatively easy to check for this case as well, because if I look at the intersection of all 3 of them, the intersection is going to be empty. And so the probability of the intersection of all 3 of them is 0. However, the probability of each of these individual events occurring is not 0. So when I multiply the 3 probabilities together, I'm not going to get 0. And so therefore, if we go back to this formula will fail for these 3 sets, even though they're pairwise independent, right? So this example shows that these notions are actually distinct things and they're not the same. Right, and so sort of intuitively, what's the idea behind what's going on here? Well, as I said before, E3 is the event where exactly one of the first or third flips is heads, but not both. However, let's assume that E1 and E2 occur. Well, the intersection of E1 and E2 is exactly the event where both the first and the last flips are H. And so sort of assuming that occurs, that means that E3 can't occur, right? So assuming that you know information from both E1 and E2 influences what can happen relative to E3, even though just knowing E1 or E2 individually does not influence E3, right? So it's possible that if you know more than one event together at the same time, that can influence a third event, even though individually the 2 distinct events don't necessarily influence the third. This is sort of what's going on. It's a little subtle, and it takes a little bit of time to get used to, but it's good to see an example like this, and hopefully that clarifies it. Great. Okay, and so so that's about it for the examples related to independence that I wanted to talk about. So I guess I didn't mention this before, but there are plenty of more other examples in the textbook which I would recommend reading as well. So I'm intentionally designing my slides so that I'm not just copying and pasting from the book, so you have other examples to look at. So the next topic is sort of one of the more important probability distributions, which is not the uniform distribution, which is the binomial distribution. And so this will involve some concepts from combinatorics that we talked about in chapter 6. And so I'll begin the next lecture on Wednesday's lecture by talking about the binomial distribution. So that's it for today.